Alright, let's go. Number 10. The observation that ends everything. Alan Guth was not looking for an ending. In 1979, at SLAC in California, he was trying to solve two nagging problems in Big Bang cosmology: why the early universe looked so uniform, and why it appeared spatially flat. His answer, published in 1981 in Physical Review D, was inflation, a brief period of exponential expansion. He was solving a puzzle. He was not predicting our death. Inflation was supposed to end. The inflaton field would decay, seed our universe, and the process would be finished. But Andre Linde at Stanford, Paul Steinhardt at Princeton, and Alexander Vilenkin at Tufts realized independently, between 1983 and 1986, that inflation does not end everywhere. In most of the meta-universe, it never ends at all. Ours is one bubble, one region where inflation stopped. There are others. Vilenkin published the Eternal Inflation Framework in Physical Review D in 1983. Linde's 1986 paper in Physics Letters B, Eternally Existing Self-Reproducing Chaotic Inflationary Universe, made the mechanism explicit. Each bubble universe cools with slightly different physical constants: a different Higgs vacuum, a different fine structure constant, a different electron mass. When two bubbles collide, the interface is a domain wall traveling outward at the speed of light. The comforting answers all die on inspection. The wall might be too far away, but eternal inflation is by definition eternal, and bubbles nucleate everywhere in phase space. It might miss us, but a domain wall is a two-dimensional structure, and any bubble intersecting our light cone sweeps our entire past into it. It might be forbidden by observation. Matthew Kleban's group at NYU published detailed collision signatures in the CMB in a 2011 paper in the Journal of Cosmology and Astroparticle Physics. WMAP and Planck team members searched. They ruled out large, close collisions. They did not rule out smaller, farther ones. The wall is not violence. It is a change in the laws themselves. Electrons weigh slightly more. Chemical bonds unravel. Your body dissolves not because anything struck it, but because the physics that assembled it no longer holds together. It travels at the speed of light. No signal precedes it. The question is not whether it will arrive, but whether it already has, one Planck time away. Not every ending arrives as violence. Some arrive as slow arithmetic. Number 9. Phantom energy accumulation. In 2002, Robert Caldwell at Dartmouth was studying quintessence, a class of dark energy models where the dark energy field can evolve over time. He was looking for a way to reconcile observations with theory. He was trying to make cosmology consistent, not apocalyptic. Standard cosmology puts dark energy's equation of state at exactly W equals -1, a cosmological constant. That value keeps expansion accelerating forever, but never diverging. Everything above -1 is safe. The line at -1 is called the phantom divide. Caldwell noticed the divide has no theoretical wall. Nothing prevents W from being less than -1. His 2002 paper in Physics Letters B, A Phantom Menace, Cosmological Consequences of a Dark Energy Component with Supernegative Equation of State, gave the phenomenon its name. If W drops below -1, the energy density of empty space increases as space expands. The vacuum feeds itself. Caldwell, Kamiankowski, and Weinberg followed up in 2003 in Physical Review Letters with the endpoint, a finite time singularity, the Big Rip. Attempts to forbid phantom energy have failed one by one. Null energy condition violations were once thought impossible. Quantum field theory produces them routinely, in Casimir experiments and squeezed vacuum states. Some argued phantom fields would immediately decay through quantum instability, but Sean Carroll, Mark Hoffman, and Mark Trodden showed in Physical Review D in 2003 that specific classes of phantom fields are stable. The DES survey initially favored BEBU equals -1. The DES collaboration, releasing results in April 2024, found preferred values in the range W0 agod -0.7 to -0.9, with WAA strongly negative, combined evolution consistent with a phantom crossing. If that crossing has already occurred, the Big Rip has a specific date. Galaxies unbind 60 million years before the end. The solar system unbinds 3 months before. Atoms unbind in the final 10 circumflex 19 seconds. The date is not unknowable. It has not been calculated with the precision the measurements now permit. The DESE data is preliminary. If confirmed, one number in one table sets the day your atoms come apart. Then there is the ending nobody can see, because it happens from the inside of everything. Number 8. The black hole information paradox end state. Stephen Hawking was, in 1974, trying to understand how black holes behaved in quantum field theory. He was extending work by Jacob Bekenstein at Princeton on black hole entropy. The math was supposed to confirm what everyone assumed. Black holes are inert. They swallow things and hold them forever. In quantum mechanics, unitarity is sacred. Every operation preserves information. You can scramble a book by burning it, but in principle, if you tracked every photon and every particle, you could reconstruct every word. This is the deepest known symmetry in physics. Hawking's calculation showed black holes radiate, and the radiation is thermal, random. It carries no information about what went in. Hawking's 1975 paper in Communications in Mathematical Physics, Particle Creation by Black Holes, made the argument formal. A solar mass black hole evaporates in 10 circumflex 67 years, a supermassive one in 10 circumflex 100. At the endpoint, the black hole is gone, and with it, according to Hawking's own math, everything it ever swallowed. Every proposed resolution has cost something. Information leaks out slowly, in subtle correlations, the Page curve, proposed by Don Page in 1993, but requires non-local physics we cannot verify. Firewalls, proposed by Almheri, Marolf, Polchinski, and Sully in 2013 in the Journal of High Energy Physics, preserve information but destroy the equivalence principle. Remnants, stable Planck mass leftovers, violate entropy bounds. Soft hair, Hawking's final proposal in his last paper before his death in 2018, has not been shown to encode enough information to close the accounting. If information is truly destroyed at evaporation, unitarity fails, and if it fails at the endpoint of a black hole, it may fail everywhere at the Planck scale. The rules governing the universe are not laws. They are effective approximations, and every quantum event you experience is only probably consistent. Somewhere in the observable universe, a small primordial black hole is finishing its evaporation. If Hawking was right in 1975, and not in 2018, information is dying inside it as you read this. Not all threats are cosmic in scale. Some are already riding on gravitational waves in our current data. Number 7. Cosmic String Network Collapse. Tom Kibble at Imperial College London was studying in 1976 how phase transitions in the early universe might leave scars. He was extending Landau's work on defects in condensed matter, the same physics that produces flaws in cooling metals. He was doing solid-state physics for the whole cosmos. Kibble showed that as the early universe cooled, symmetries broke unevenly, and one-dimensional line defects, cosmic strings, could remain behind. A network of these strings would evolve, forming loops, radiating gravitational waves, and slowly decaying. The math was clean, the behavior was scale invariant, the universe stayed stable, only for a certain range of string tensions. Above a critical threshold, the network does not decay smoothly. The critical parameter is g mu, Newton's constant times the string tension. Simulations by Blanco Pilato, Olum, and Schleyer at Tufts University, published in Physical Review D in 2011, showed that below g mu = 10 circumflex 11, the network scales quietly. Above it, the loops grow faster than they radiate. The June 2023 NanoGrav 15-year dataset, published in the Astrophysical journal Letters, reported a stochastic gravitational wave background inconsistent with pure supermassive black hole mergers. The signal has been fitted with black hole mergers alone, but the amplitude sits high, and the spectral slope is difficult to reproduce that way. Inflationary gravitational waves fit worse, domain walls fit worse still. Cosmic strings at g mu = 10 circumflex 10 fit the signal well, but that value sits above the smooth decay threshold. The Ellis and Lewicki 2021 paper in Physical Review Letters spelled out the implication. If strings are the source, the network is approaching a phase transition. A phase transition in a cosmic string network releases the accumulated energy of the entire network in a single gravitational wave burst. It would not arrive as a warning. It would arrive as everything within its light cone being sheared by tidal forces on scales below the atomic. Your bones would come apart into their constituent nuclei before you registered that a wave had arrived. Nanograv's next dataset lands in 2027. Either the amplitude keeps climbing, or it does not. One graph will tell you which universe you live in. Some endings were retired decades ago, and then quietly brought back. Number 6. The Big Crunch Residual Risk. The Planck satellite team was not designed to predict the end of the universe. It was launched in 2009 to map the cosmic microwave background at unprecedented precision. The point was calibration, cleaning up the numbers on dark matter, dark energy, and the age of the cosmos. For decades, textbook cosmology asserted that dark energy is constant. Its equation of state is exactly -1. Its density does not change. The universe expands, cools, forever, but never reverses. The Big Crunch was retired in the late 1990s, when Type 1Ia supernova data from Saul Perlmutter's and Brian Schmidt's teams showed expansion accelerating. The Planck 2018 results tightened the number. They did not eliminate the possibility of change. The Planck 2018 legacy release, published in Astronomy and Astrophysics in 2020, gave W = -1.03, 7-0.03 for a constant equation of state. Dynamical dark energy models, the CPL parametrization, remain permitted well within the 2 sigma envelope. DC's April 2024 release moved the central value further from -1, with the paper by Adame and the DAISY collaboration suggesting W0 def evolution at up to 3.9 sigma from the constant W baseline. Every cosmological argument for permanence has softened. Anthropic bounds do not require dark energy to remain repulsive, only to have been repulsive long enough to permit us. Quintessence models with slowly rolling scalar fields can reverse sign in the far future. String landscape estimates by Raphael Busso and Joseph Polchinski at Berkeley in the Journal of High Energy Physics in 2000 give roughly 10 circumflex 500 vacuum states, most of which are not de Sitter. There is no theoretical reason our expansion must remain monotone. If dark energy reverses, expansion slows over billions of years and turns inward. Galaxies fall together. Temperatures climb. In the final million years, the CMB becomes brighter than starlight. In the final second, the entire cosmos is denser than a nuclear reactor. Your descendants, if you have any, would see the sky glow before they died. What color would it be? Some endings do not require any change at all, only patience. Number 5. The heat-death expansion. Rudolf Clausius was working, in 1865, on steam engines. He was trying to formalize why heat flows in one direction, from hot to cold, never back. He introduced the word entropy in a paper for the Prussian Academy of Sciences. He was doing thermodynamics for industrialists. He was not writing an obituary for the cosmos. The second law of thermodynamics says entropy in a closed system never decreases. The universe is the largest closed system. Its entropy has been climbing for 13.8 billion years. In principle, it can climb forever, but only if there is a gradient. Gradients require difference. Difference requires structure. Structure requires low entropy. The gradients are running out. Freeman Dyson's 1979 paper, in Reviews of Modern Physics, Time Without End, Physics and Biology in an Open Universe, worked through the timeline. Stellar burning ends at 10 circumflex 14 years. Stellar remnants collide or evaporate over 10 circumflex 40 years, contingent on proton stability. Black holes evaporate between 10 circumflex 67 and 10 circumflex 100 years. After 10 circumflex 100 years, the universe contains photons with wavelengths larger than the observable universe and a temperature approaching 10 circumflex 30 K. Attempts to avoid heat death have failed on their own terms. Cyclic cosmologies, Paul Steinhardt and Neil Turok's ekpyrotic model, published in Physical Review D in 2002, require the universe to reset, but reset mechanisms need low entropy initial conditions, and the second law forbids arriving at those. Loop quantum bounce models remove the singularity, but not the arrow of time. The asymptotic de Sitter state is thermal, a Hawking-Gibbons temperature of roughly 10 circumflex 30 K, but it is an equilibrium of nothing acting on anything. The universe does not disappear. It persists, cold, uniform, radiant with photons no observer will ever collect. Every memory, every love, every act ever performed, dissolves not into darkness, but into a quiet, temperature-locked forever. Heat death is not an ending. It is a state in which nothing can end, because nothing can change. What does it mean to say the universe still exists? Some endings do not end the universe, they end you, without touching the universe at all. Number 4. Boltzmann brain dominance. Ludwig Boltzmann was defending, in 1895, the second law of thermodynamics against critics who could not reconcile it with reversible microscopic physics. Writing in Nature, a letter to the editor, of all places, he proposed that our low-entropy region was a rare fluctuation in a much larger universe already at equilibrium. He was solving a technical problem in statistical mechanics. He was not proposing a nightmare. In an infinite universe at heat death, thermal fluctuations occur. Rare fluctuations produce complex structures. Extraordinarily rare fluctuations produce fully formed conscious observers with false memories of complete lives. Fully formed observers require far fewer particles than the evolutionary history of an entire cosmos. Andreas Albrecht and Lorenzo Sorbo at UC Davis published the modern formulation in Physical Review D in 2004. Can the universe afford inflation? The paper computed the entropy cost of a normally evolved observer at roughly 10 circumflex 88 units of entropy, versus a spontaneously fluctuated brain at roughly 10 circumflex 42. In an eternally expanding de Sitter universe, Boltzmann brains outnumber evolved observers by more than a factor of 10 circumflex 40 within 1 Poincare recurrence time. Every attempt to remove the paradox has failed. Sean Carroll and Jennifer Chen at Chicago proposed in 2004 that the universe never truly reaches equilibrium, but that scenario contradicts current dark energy observations. Don Page at Alberta suggested in 2006 in the Journal of Cosmology and Astroparticle Physics that our cosmological measure should exclude eternal futures, but no consistent measure has been found. Busso and Freivogel at Berkeley, writing in 2007, showed that most well-defined measures on the multiverse produce Boltzmann brain dominance as an unavoidable output. The math has been reproduced by at least 5 independent groups. No error has been located. The typical observer in the calculation is not you as you understand yourself. The typical observer has a brain that appeared 5 seconds ago with the memory of writing this sentence and will dissolve back into vacuum in another 5. There is no experiment that can distinguish between the two. The reader you believe yourself to be, what test would prove you are the evolved one? Some endings are already scheduled, buried in an atom you cannot see. Number 3. Proton decay. Howard Georgi and Sheldon Glashow at Harvard were, in 1974, trying to unify the strong, weak, and electromagnetic forces into a single mathematical structure. They wanted elegance. They wanted the Standard Model's messy 3 forces to collapse into one. Their ACU-5 Grand Unified Theory achieved that goal in a paper in Physical Review Letters. The Standard Model treats the proton as stable. Charge conservation, baryon number conservation, and the absence of any lighter baryonic state combine to make it eternal. Every atom in your body relies on this. The half-life of a proton, in the pure Standard Model, is effectively infinite. The moment quarks and leptons occupy the same multipled, baryon number is no longer sacred. Georgi and Glashow's original SU-5 predicted a proton lifetime near 10 circumflex 29 years. The Super Kamiokande experiment in the Kamioka mine in Japan has been running since 1996, watching 50,000 tons of ultra-pure water for the flash of a decaying proton. The 2020 results, published in Physical Review D by the Super K collaboration, set the lower limit at 2.4 x 10 circumflex 34 years for the Ptrom E plus Pi0 channel. Minimal SU-5 is dead. So 10 and supersymmetric variants predict lifetimes between 10 circumflex 34 and 10 circumflex 36 years, inside the reach of the next generation of detectors. The absence of decays has not saved the proton, it has only eliminated the fastest models. Baryon number conservation, as an exact symmetry, has no theoretical justification. Steven Weinberg pointed this out in Physical Review Letters in 1979. Sphaleron processes in the electroweak sector already violate baryon number in the Standard Model itself, without any grand unification. String-inspired models generically predict decay in the 10 circumflex 33 to 10 circumflex 36 year range. There is no consistent theory that forbids the process, only ones that delay it. If protons decay, then every atom in every body that has ever lived has a scheduled dissolution date. Not violent, not immediate, but real. Your matter is on a countdown. Somewhere in Japan, right now, a technician is watching a screen. If a pixel flashes, the countdown is confirmed. Some endings dismantle everything in months, some in seconds. Both are closer than we think. Number 2. The Big Rip. Robert Caldwell at Dartmouth, along with Mark Kamiankowski at Caltech and Nevin Weinberg then at Berkeley, were following up in 2003 on Caldwell's earlier phantom paper. They were not writing about the death of the universe. They were exploring how a mildly exotic dark energy component would reshape late-time cosmology. Standard dark energy with W equals -1 gives asymptotic de Sitter expansion, stretching forever, but never so violently that bound structures come apart. Galaxies stay galaxies. Solar systems stay solar systems. Atoms stay atoms. Below W equals -1, the Hubble parameter itself diverges in finite time. The stretching becomes lethal. Their paper, Phantom Energy, Dark Energy with W-1, Causes a Cosmic Doomsday, appeared in Physical Review Letters in 2003. For W equals -1.5, they calculated the timeline explicitly. The Milky Way unbinds 60 million years before the end. The solar system dissociates 3 months before. Earth explodes 30 minutes before. Atoms unbind in the final 10 circumflex 19 seconds. Every stage is set by a single equation of state number. The wall against W-1 has not held. Quantum gravity effects have been proposed as a barrier, but no calculation shows they intervene at the required timescales. Modified gravity, FR models, DGP Brandworld models, can mimic phantom behavior without explicit phantom fields, sidestepping the theoretical objections. The DS Year 6 supernova sample, released in 2024, and the Desi-Baum results from the same year, together suggest W evolving from a value near zero toward a value more negative than -1. The measurement is not conclusive. It is not comforting either. Under a phantom equation of state, the end is not thermal, not cold, not slow. It is mechanical. Your body is pulled apart by the expansion of space between its atoms. Your last conscious moment is one in which your skin is being stretched faster than any signal can traverse it. The date is a function of W and WA, 2 decimal places away from a value that has already been measured, and the one that needs no warning, only a single quantum event. Number 1. False vacuum decay. Sidney Coleman at Harvard was not thinking about the end of the universe in the late 1970s. He was doing formal quantum field theory, calculating tunneling rates for scalar fields, extending Euclidean instanton methods from the work of Polyakov and 't Hooft. He was writing lectures. He was solving a technical problem in gauge theory. The vacuum, in quantum field theory, is defined as the lowest energy state of every field. It cannot be undermined. Anything below it does not exist. The universe rests on it. Coleman realized the observed vacuum could be a local minimum, with a lower, true vacuum hidden behind an energy barrier that quantum tunneling could cross. Coleman and Frank DeLuca's paper, Gravitational Effects on and of Vacuum Decay, published in Physical Review D in 1980, calculated the rate. A bubble of true vacuum, once nucleated, expands at exactly the speed of light. Its interior is incompatible with the standard model. No atoms, no chemistry, no light as we know it. In 2013, Butasso, Degrassi, Giardino, Giudice, Sela, Salvio, and Strumia, publishing in the Journal of High Energy Physics, calculated using the measured Higgs mass near 125.1 GeV and top quark mass near 173.3 GeV that our vacuum sits in the metastable region, stable enough to last longer than the current age of the universe, but not stable. Every proposed escape has narrowed. Beyond standard model physics could stabilize the Higgs potential, but the LHC has found no new particles up to the multi-TeV range. The metastability calculation could be wrong at higher loop orders, but 3 independent groups have reproduced it. The lifetime could be effectively infinite, but effectively is a probability distribution, and the tail extends into the present. Anthropic reasoning offers no protection. We exist because the decay has not happened yet, not because it cannot. The bubble is preceded by nothing. It travels at sea. There is no photon, no gravitational wave, No signal ahead of it. You are not warned. You do not see it arrive. Your last state is unchanged. Your next state does not exist. The nucleation rate is a probability per unit spacetime volume. It is non-zero. Somewhere in the observable universe, in the next second, is it? None of these threats sit at the frontier of physics. They sit at the center, inside the equations we trust most, in the parameters we measure best, in the theories that pass every experiment we can build. The universe is not confused. It is behaving exactly as its laws prescribe. The problem is that its laws include as boundary conditions endings we cannot detect, cannot outrun, and cannot prove have not already begun. If you want to see more videos like this, click the video on screen now.